There are several different types of F-tests, and the name of the F-test tells us a lot about the research design. So some F-tests are used for testing assumptions of parametric tests, others are used for analyzing mixed designs, while others are used when we have multiple independent variables, or even sometimes we have F-tests that have multiple dependent variables. We'll also learn about a regression F-test when we do Module 6, but for right now in Module 5, we'll be concerned about two different types of F-tests, the ANOVA model, in particular the one-way between groups ANOVA and the one-way within groups ANOVA. Now, again, like I said, the name tells us something about the research design, and so the ANOVA insignia tells us that the F-test is an analysis of variance, that we're not directly comparing the means of our groups, but rather we're comparing the variance of our groups. Now, when we say we have a one-way ANOVA for our F-test, we're saying we have one independent variable. Now, that independent variable may have multiple levels, but we have one independent variable. So in particular, maybe we were interested in researching differences in class standing, so whether students were freshmen, sophomore, juniors, or seniors, class standing would be one independent variable that has four levels or four groups. And so we compare those four groups, freshman, sophomore, junior, senior, but there is only one independent variable. Now, if I had a two-way ANOVA, then that would mean I had two independent variables. And so maybe I'm looking at class standing and social economic status, where SES has three levels. And so I have two independent variables, one with class standing that has four levels, and then one with SES that has three levels, maybe low, moderate, or high SES. And so in that case, I have two independent variables. I have a two-way ANOVA. Now, if I have a two-way ANOVA with four levels and with independent variable with four levels, and then another independent variable with three levels, then I have 12 groups. I have three levels of SES for every level of class standing. So sometimes you'll hear that be called a 3x4 ANOVA. So that's another terminology. The 3x4 tells us we have two independent variables, one with three levels and another one with four levels. And if we multiply those two together, we have 12 groups total. So typically we're not going to have any more than about three independent variables. So you can have four-way ANOVAs and five-way ANOVAs, but typically you won't. Typically you'll see one, two, or three-way ANOVAs. The reason for that is that we're cognitively limited. So we're three-dimensional beings. We tend to see in three dimensions, and each of our independent variables serve as a dimension. So once we get to four dimensions or four independent variables, it becomes very difficult for us to comprehend and very difficult for us to interpret. And so usually we're limited to about three independent variables for an ANOVA F-test. If you see the terms between groups and within groups in the ANOVA name or the F-test name, then you should already know what those two terms tell you. We've talked about it before with the independent and paired sample t-test. That if I have an independent sample t-test, then I have a between groups design. In other words, every observation is measured once and only once for each of the groups. Whereas if I have a within groups design, much like a paired sample t-test, then my observations are being measured more than once. And so maybe I measure the same people multiple times, 3, 4, or 5 times, in which case I might do a within groups ANOVA. So the between or within groups ANOVA tells us something about the research design. It tells us if the observations are being measured once and only once, or if they're being measured multiple times, similar to an independent and dependent sample t-test. So let's go ahead for this lecture and focus on the one-way between groups ANOVA. We'll get to the within groups ANOVA in another lecture. In a one-way between groups ANOVA, we're going to have one independent variable. That's what the one-way tells us. And that one independent variable may have multiple levels. So for example, let's say we're looking at testing a new drug on pain relief. And so we may test this drug with three different groups. And so our independent variable is the drug condition or the drug type. And we may have three different conditions, such as one condition with participants with no drug, another condition where participants receive a placebo, and then a third condition where participants get the actual new drug. And so here we have three different levels, but only one independent variable, and that's the drug type. So the between groups part of it tells us that each participant in our study is in one and only one of our groups. So in other words, if we have a participant named Kelly, and we were to have her participate in the study, Kelly would either receive no drugs, or she'll be in the placebo condition, or she will receive the new drug, but she will not be in more than one of those groups. She'll just be in one of those groups, and so we would randomly assign her to one of those groups. So that would be an example of a one-way between groups ANOVA. We have one independent variable, 3 levels, and our participants are in one and only one of the groups. They won't be in multiple groups. They won't be tested with multiple types of drugs. The assumptions for a one-way between groups ANOVA should look very familiar to you because they're exactly the same as an independent sample t-test. And so there really isn't anything new to remember as far as the assumptions. However, theoretically, we should still talk about the last two, which we will because there are some differences. But for the most part, there's not much that's new here with the assumptions. The first three are the same as they've been for all of our parametric tests that we've learned this semester. The fourth one is also similar to independent sample t-test, that the population difference between the means should be 0. And again, that's based on the null hypothesis. And then the last one is one that we've already talked about, is that our participants should be in one and only one of the independent variable conditions, or in other words, one and only one of the levels of the independent variable. Now, like I said, we should talk about the last two assumptions, at least briefly. So let's talk about the fourth assumption. The population difference between the means should be 0. Now, just like an independent sample t-test, this assumption is based on the null hypothesis. So let's use our example of type of drug and its effect on pain. And so we have three conditions. We have the none condition, where our participants don't receive any type of medication. They don't receive any placebo. They just come in. We measure the amount of pain they have. And then we have a placebo condition, where our participants are given an inert substance, so something that's not going to make them feel better, but may make them psychologically think that they're better. And then we'll have the third condition, where we actually give participants the new drug. And so again, participants are in one and only one of these particular conditions, and then our dependent variable is the amount of pain that they're in. And so our null hypothesis is that if this drug has no effect, if the type of drug has no effect on pain relief, then there shouldn't be a difference among our groups. In other words, the means of each of our groups should be the same. And so our null hypothesis is that there's no difference in pain between the drug conditions. So in this particular example, because we have three different conditions or three different levels, we have what's called multiple comparisons. So we have one comparison where we compare the group that doesn't get anything, we just measure their pain, that's the none condition, versus the placebo condition. We can also compare the none condition versus the new drug condition. And then we can also compare the placebo condition or group with the new drug group or the new drug condition. And so if we ever wanted to know the number of comparisons for a study based on the levels of the independent variable, then we can take the formula of k times k minus 1 divided by 2. And k equals the number of groups that we have, or the number of samples. So in this case, we have 3 groups or 3 samples. So we'll take 3, multiply it by k minus 1, which is 2. That gives us 6. And we divide by 2, and that gives us 3. So you should be able to get the number of comparisons based on the levels of the independent variable. So for another example, if I had 4 levels in my independent variable, then I would take 4, multiply it by 3. That would give me 12. And divide by 2. And so my total number of comparisons then would be 6. So if I have 4 levels of my independent variable, I'd have 6 comparisons. So again, practice with the formula. You should be able to get the number of comparisons based on the levels of an independent variable. So the last assumption you already know. We've already talked about it. We've seen an independent sample t-test. We've already talked about it today here in the lecture. But let's just visualize it really quick. Here's our drug levels, and so we have the none condition, the placebo condition, and the new drug condition. And so I might have Samantha, Greg, Hannah, and George in the none condition. We're not receiving any type of medication, not receiving a placebo. We're just measuring their pain. Then I might have Alex, John, Karen, and Joy in the placebo condition. And then I might have Travis, Susan, Ginny, and Gerald in the new drug condition, where I give them the drug and then measure their pain. And so in this case, you'll notice that there are different individuals in each of the groups. They're not related in any particular way. They're what we call independent. And so each observation, in this case people, are in one and only one of the groups. So this would be a between groups design. This would meet that last assumption that our participants are in one and only one of the levels of the independent variable. Here is the F statistic equation. You'll notice in the numerator that we have the variance between the groups, and then in the denominator we'll have the variance within the groups. So remember, this F-test is an ANOVA F-test. It's an analysis of variance, and so we're going to have variances in our equation. So it'll be a ratio of variances between the groups divided by within the groups. So we use the symbol MS for variance in an ANOVA. So MS stands for variance. It's actually mean squared. So remember, when you calculate your variance, you take each observation, you subtract the mean, and then you square it. So that's variance, and so that's the same thing as MS, or mean squared. So we'll take the mean squared between, the variance between the groups, and divide by the mean squared within, or the variance within the groups. And that's our F statistic equation. In our previous statistical tests, we always had the numerator be the means of the groups, where we're subtracting the means. Well, we can't do that here with an F-test because we have more than two groups. We have multiple groups, 3 groups, 4 groups, 5 groups. It doesn't really matter. You can have as many groups for an F-test, and so we can't subtract the means for a very practical reason. That practical reason would be if we used the means and subtracted the means, then the order of the subtraction would matter. And so let's go back to our example with the pain relief drug. And so we have our participants in the no drug condition, and they have an average pain rating of 7, where higher scores is more pain. And then we have the placebo condition, where their average is 5, and so psychologically, because they're given something, even though it may be just a sugar pill or a saline shot, they think that something's happening, pain is being relieved, and so they might report a 5. And then in the actual new drug condition, they may report a 3, and so pain is being relieved in comparison, in what appears to be in comparison to the placebo and the none condition. But if we were to subtract the means, then the order of that subtraction would matter because we have 3 groups. And so maybe we take our mean for the none condition, 7, and we subtract 5, the mean from the placebo, and we subtract 3 from the mean of the new drug, and we get a number of -1. But what if we changed the order and we started with the new drug, then subtracted the placebo mean, and then the no drug mean? And if we did that, we'd take 3 minus 5 minus 7, and now we get -9. And so the order of subtraction matters, that how we subtract the means gives us different results. So it's unreliable. We can't use the means of our groups in our equation, at least not in its current form. So again, if we did a different order, and so we took the placebo minus the new drug minus the none condition and subtract the means from those 3 groups, now we get yet a different value of -5. And so the differences among our means can't be -1 and -9 and -5. We should get the same number. And so we can't subtract means when it comes to our F statistic formula. So instead, we'll use the variances between the groups. So we won't subtract the means, so we won't look at the differences between the means. We'll look at instead the variances among our groups. And that's what the MS between stands for in our equation, the variances between the groups in our study. So here's our formula one last time. So again, in the numerator we will not be subtracting means, rather we'll be looking at the variances between the groups. In the denominator we'll have the variance within the groups. Now, even though we're using the variance in the denominator, the idea is still the same with our other statistical tests, such as the t-test and the z-test. In the t-test and the z-test, we used the standard error, but that was still a measure of variability within the groups. And so we're just going to change it from standard error to variance, and we'll still have a measure of variability within the groups for the denominator. Alright, so that's the basics, conceptual foundation for the F-test. When we go into class, we'll go ahead and go through an example of an F-test, and we'll touch on these topics again as we go through that example. Alright, thank you again for your time, and I'll see you in class.